This video introduces the idea of stereoisomerism in the context of the alkenes, which show a particular form of stereoisomerism, often called EZ or sometimes cis-trans, very closely related to each other. By the end of the video, you ought to be able to explain why it is that alkenes can show EZ or cis-trans isomerism, but be able to also spot when alkenes do or don't shall have EZ isomers. You ought to be able to label pairs of isomers as either E or Z or cis or trans, and you ought to, given one other pair of isomers, be able to draw the other isomer of the pair. Before we move on and look at this specific type of isomerism, let's just remind ourselves what we mean by isomers in general. And so there's a definition that you need to be confident and familiar with, that isomers are molecules with the same molecular formula, but they have different structural formulae. To remember how this works out in practice, let's look at one molecular formula, C5H12, 5-carbon alkane. Pause the video for a moment and try and sketch out a few different structures using skeletal formulae for this molecular formula. And so maybe you sketch the straight chain, 5 carbons, so pentane. Took it down to 4-carbon chain with a 1-carbon branch, methyl butane, or even a 3-carbon chain with 2 methyl branches, so dimethyl propane. So these are all isomers of each other. They all share the molecular formula C5H12, but they have different structures. And these are what we call structural isomers. Turning our attention to the alkenes now, the alkenes also can show this structural isomerism we've just mentioned. So for instance, if we have the alkene hex-1-ene, we could slide that alkene group along the chain, have hex-2-ene, and both of these molecules are clearly isomers of each other. They share the same molecular formula. We could also attach some chlorines, and then we could rearrange things so that both chlorines were attached to the same carbon. Again, within the pair, they're isomers of each other. They'd share the same molecular formula. So we've been talking about structural isomerism. What do we mean then by stereoisomerism? And what we'll see is that stereoisomers are a rather more subtle form of isomerism. When you look at a pair of stereoisomers, which we will do in a moment, you'll see the atoms are connected in the same sequence. But what varies between the isomers is that certain atoms or groups of atoms are oriented differently in space. So in other words, they might be pointing in different directions when we look at them in 3 dimensions. Let's look at an example then. Take this alkene. What would be a stereoisomer of it? Well, what wouldn't be a stereoisomer would be to chop off any atom or group of atoms and move them somewhere else in the molecule. Stereoisomers have atoms connected in the same sequence. So this would be a stereoisomer, and if you look at it, you can see that each end of the double bond both has 1 hydrogen and 1 chlorine, so nothing's changed in that regards. But what has changed, especially if you consider the chlorines or the hydrogens, is where things are pointing. So for the top alkene, both chlorines are pointing down, whereas for the bottom chlorine, one is pointing down and one is pointing up. The particular type of stereoisomerism that we're going to be looking at, EZ or cis-trans, applies to alkenes, but it doesn't apply to alkanes, and you need to understand why. Let's consider what we actually mean by an alkene group in terms of the sigma and pi bonds that you should already have been introduced to. So a carbon-carbon double bond, an alkene group, consists of 1 sigma bond, a shared orbital between the carbon nuclei, and then one pi bond, which consists of a pair of shared orbitals, one above and one below the sigma bond. Now, the presence of that pi bond prevents each end of the alkene group twisting or rotating compared to the other end. Because to do so, and if we consider what that would look like, if we twisted one end round, so the right-hand end, so the hydrogen points up, and the chlorine points down. If you can think about it, the only way that would happen would be for the pi bond to have broken and to have then reformed again. So to twist or rotate the ends of an alkene group requires the breaking of the pi bond, and so that doesn't normally happen. For the sake of comparison, let's look at the bonding between 2 carbons in an alkane. And if you remember, a single bond consists of just a sigma bond, a pair of electrons shared between the 2 carbon nuclei. And there's nothing now to prevent the carbon atom with the groups attached at each end rotating round. A sigma bond allows free rotation because nothing needs to break in order for that rotation to occur. I could draw the same molecule with the right hand end twisted round slightly, so the chlorine points up now instead of down, and those two molecules are identical to each other. In a way, all they represent is different moments in time. The groups at each end will be spinning round freely, and so these two are identical to each other. Having said that alkenes can show this EZ or cis-trans stereoisomerism because of the presence of the carbon-carbon double bond which prevents the groups at each end rotating, does that mean that all alkenes will show it? And the answer is no. And the best way to prove that is to look at an example. Take this molecule here. At the left-hand end of the alkene group, we've got two hydrogens attached. At the right-hand end, we've got one chlorine and one hydrogen. And if I draw the molecule again with the groups at the right-hand end swapped over, so the hydrogen's now pointing up and the chlorine's pointing down, could we describe these as a pair of stereoisomers? Well, if you take a look, hopefully you'll see that no, you couldn't actually, because in reality this is just the same molecule flipped over on the page. So we have two conditions we have to meet for an alkene to show this EZ or cis-trans stereoisomerism. First, we have to have the carbon-carbon double bond, with which therefore prevents the groups at each end rotating freely. But secondly, each end of the alkene group, each carbon involved in the alkene group must have two different groups attached, two things that are not identical to each other. So the problem here is at the left-hand end of the alkene, we have two hydrogens, two things that are exactly the same as each other, and therefore this alkene will not show the EZ or cis-trans stereoisomerism. This condition of needing two different groups attached to each end of the double bond can cause people to fall into a trap sometimes. And the best way to counter that is to look at an example. So take this pair of molecules and let's consider whether they will or won't show the EZ or cis-trans stereoisomerism. The first condition is that you have to have a carbon-carbon double bond. Well, they both do, so that condition has been met. The second condition is that each end of the carbon-carbon double bond, two different groups are attached. And the mistake to make here would be to go, well, each end is attached to two carbons, and those carbons are identical to each other, so therefore this won't show the EZ or cis-trans stereoisomerism. But what you actually need to do is look at the two groups in their entirety. So it doesn't matter which end we think of here, the left-hand end or the right-hand end of the alkene group. One thing attached is a one carbon methyl group, whereas the other group attached has two carbons in it. So these two groups are not identical to each other. We've met the conditions. We have the carbon-carbon double bond and we have two different groups at each end. And so these now are genuinely a pair of isomers and not just the same molecule spun or flipped round in some way. Let's turn our attention now to how we label these pairs of isomers, and this is where the EZ or cis-trans that I keep mentioning comes in. We'll consider the EZ system first, and the best way to do that is in the context of an example. So have a look at this simple alkene here. It's got the carbon-carbon double bond that prevents rotation, and each end of the double bond has two different groups attached, an H and a CH3. So it fits with our requirements for this form of stereoisomerism. If you look at this molecule in a bit more detail and you consider the hydrogens, what we can spot is that at the left-hand end, the hydrogen points up on the side above the double bond, and at the right-hand end, the hydrogen points down on the side below the double bond. So we say the H's are on opposite sides of the carbon-carbon double bond, and we give it the label E. If you're wondering where the E comes from everything I've just been saying, it actually comes from German. In German, the word entgegen means opposite. And so when the isomer has similar groups on opposite sides of the double bond, we give it the letter E. Drawing the other isomer of this molecule, now we can see at the right-hand end, we've swapped the two groups round, so the H is pointing up. And so now, describing this molecule, we can say that both hydrogens are on the same side of the carbon-carbon double bond, and that gets the tag Z. Z again coming from a German word zusammen, meaning together. So looking at a pair of isomers, the one which has similar groups on opposite sides of the double bond is the E isomer, and the one that has similar groups on the same side of the double bond is the Z isomer. Just be very careful when you describe this about the language you use. You must use the word side rather than end. So don't say they're on the same end or opposite ends, because when we use the word end, we use it conventionally to refer to the two different carbons. So if you look at both these two molecules, both of them have the hydrogens at opposite ends. Nothing's changed there. But one has them on opposite sides, the other one has them on the same side. Well, the best way to make sure this makes sense is to look at a couple of examples. So take this pair of molecules here. Maybe you're already feeling that this system makes sense, so pause the video and see if you can decide which one would be the E isomer, which one would be the Z isomer, and to be able to explain why. And if you're right, you'll have come to this conclusion. The one on the left is the Z isomer, Z meaning together, and so it doesn't matter whether we talk about the fluorines or the hydrogens. Let's talk about the hydrogens. Both the hydrogens are together on the same side of the double bond. They both point below it. For the molecule on the right, they're now on opposite sides of the double bond. The hydrogen on the left end is pointing up, and the hydrogen on the right end is pointing down. To add a bit of extra difficulty, these two molecules have been drawn in the skeletal form. And again, the challenge is to decide which is the E and which is the Z isomer. The mistake to make here is to go, well, hang on, each end's only got one group attached. Well, don't forget, in skeletal drawing, you don't show hydrogens that are attached to carbons, and carbon always forms 4 bonds. So you need to sort of mentally fill in as many hydrogens as necessary to give each carbon in the molecule 4 bonds. So have a look, have a think, see which one is E or and which one is Z. Pause the video and see if you can decide. And if you're right, you'll have come to this conclusion. The left-hand molecule is the E isomer. On the carbon at the left of the double bond, the hydrogen would be pointing down, whereas the carbon at the right of the double bond, the hydrogen would be pointing up. So the hydrogens are on opposite sides, entgegen, so E. The right-hand molecule, at each end of the double bond, the hydrogen is pointing on the sort of downside of the double bond, so they're together, zusammen, so this is the Z isomer. Here's another pair of molecules drawn in the skeletal style. Have a look at these, see what you make of them in terms of E and Z isomers. Pause the video and have a think. Well, you might have spotted that this is a trick question. These two are just identical molecules. In each case, the right-hand carbon of the double bond just has 2 hydrogens attached. So it doesn't fit the rules. Yes, it does have the carbon-carbon double bond that can't rotate, but no, at each end there aren't 2 different groups attached. So these are just identical molecules, spun round, flipped over a bit, but not a pair of isomers. As well as being able to label a pair of isomers as E or Z, we might want to be able to draw the isomer of an alkene given its structure. So let's look at how to do that with an example. Take the alkene here. It fits the requirements to show EZ isomerism, and if you look at it carefully, you might see that it's the E isomer. The H's are on opposite sides of the double bond. So how would we go about drawing the Z isomer of this molecule? Well, it's a very simple trick. Just keep the groups at one end of the double bond in the same positions, but at the other end of the double bond, flip their positions. So this is now the Z isomer. And if you look at the right-hand end of each molecule, you can see that I've swapped over the positions of the two groups. The left-hand ends of the two molecules have stayed exactly the same. Let's look at that with the second example. This time drawn skeletally, because that can be a little bit more confusing, but the principle remains the same. This would be the E isomer again. So to draw the Z isomer, we want to swap over the groups at one end of the double bond. But I suppose the slightly strange thing here is you can only see one group at each end of the double bond. So you might think, well, you know, what's to swap? But of course, being skeletal, there's the undrawn hydrogens there as well. So if I start drawing the molecule, to get the Z one, we'll keep the left-hand end the same. It doesn't matter which end you keep the same, just going with the left-hand end. And then when we get to the right-hand end of the double bond, I'm going to want to swap the position of the ongoing chain with that of the invisible hydrogen. So where in the left-hand molecule the chain carries on pointing downwards after the double bond, I'm going to point it upwards. And then we have a second carbon to add. Now, it really doesn't matter where which direction I point that in, so I'm just going to sort of zigzag onwards, but it's only really the point where it attaches to the double bond that we have any concern for, and so that would be the Z isomer. So once again, the best thing we can do here is to have a go at one or two examples to make sure this is well understood. So the challenge here is for the alkene shown, draw the other isomer, and then label the two isomers as E or Z. Pause the video and have a go. So one option would have been to draw the other isomer as shown here. I've chosen to keep the left-hand end of the double bond the same and swap the position of the groups at the right-hand end. But you could have kept the right-hand end the same and swapped the positions at the left-hand end. That wouldn't have made any difference. And the labels are Z for the first isomer, the hydrogens are on the same side of the double bond, and E for the second isomer, the hydrogens are on opposite sides of the double bond. So here's another alkene to think about. Pause the video and see if you can draw the other isomer of an EZ pair and label the structures accordingly. And you have probably spotted that it's a trick question. There is no other EZ isomer. The right-hand end of the alkene group has got two CH3 groups attached, two identical groups, so it won't show EZ isomerism at all. This one, I promise, is not a trick question. Another molecule to try your hand at. Pause the video, draw the other EZ isomer and label both structures as E or Z accordingly. So the matching structure could be this. Again, I've just chosen to keep the left-hand end the same and swap the groups at the right-hand end. You might have done the opposite, it wouldn't make any difference. And the labels should be E for the first molecule and Z for the second molecule. All of our recent discussion has been about EZ isomerism, but if you remember back to the beginning, I was talking also about this stereoisomerism being called cis-trans. And so when you see how those systems compare, and effectively, as far as you're concerned, you can just match up that cis means the same as Z, and trans means the same as E. So the same sort of principles apply, but instead of labeling an isomer Z, you could label it cis. Instead of labeling it E, you could label it trans. And if you want a way of remembering that, the best thing people seem to come up with is to say cis same side, so all the kind of sounds, and then Z same side. Yeah, a bit of a stretch, but it's the best we could think of. So let's just see that in action. A pair of molecules, the first one on the left there being the E isomer, so we call it the trans isomer, and the one on the right being the Z isomer, so we call it the cis isomer. Have a look, just make sure that makes sense to you. Some of you might have started wondering what would happen if you had a carbon-carbon double bond with four completely different groups attached. How could you say two things were on the same side or opposite side? Well, in reality, this goes beyond the demands of the A-level course. But just as a final thing, we'll take a look at it and see the basic principles at work here. In each case, these alkenes at the left-hand end have a bromine and a CH3 group, with a carbon attached to the carbon at that end of the double bond. And at the other end, they have a hydrogen, not shown because of the skeletal diagram, but I filled it in there, and also an ongoing carbon chain. So how do we compare things here? Well, it might be tempting to look and go, oh, look, there's carbons on the opposite sides of the double bond. But actually, the way this works is to consider, as you head out from the double bond at each end, the heaviest thing that you come to first at each end. So on the left, it would be the bromine atom is heavier than the carbon atom that you meet first. And on the right, the carbon atom is heavier than the hydrogen. So actually we see these two heaviest atoms are on the same side of the double bond, so this would be the Z isomer. Looking at the left-hand molecule, again at the left-hand end of the alkene group we've got a bromine, and we've also got a methyl group with a carbon attached there, and at the right-hand end we've got a hydrogen attached which I've filled in, and another carbon for the ongoing chain. And so again, thinking about which atom is heaviest at each end, now we see that they're on opposite sides of the double bond, and so this is the E isomer. If there was no difference for the first atom you get to heading out with the two groups at one end of the double bond, you simply move on to the next one and the next one until you find the first possible difference. But like I say, that's beyond the demands of the A-level course, and so don't worry about it.